Thanks a lot for the introduction, and hello everybody. This is going to be a review of searches for long-lived particles with CMS. And in order to get started, let me try to highlight one of the key results of the LHC event 2 data. And to me, these are the measurements of the Higgs properties. And this is nicely summarized in this plot here that you see here that show the measurement of the couplings to third generation fermions here in red, in black to effector bosons, and then recently there was the evidence of the coupling to the muon. And what is remarkable is what you see in the ratio pad, that this is the agreement with the standard model prediction, that you see that this is fantastic over several orders of magnitude. So while this was really a great achievement, the Higgs discovery did not really address many of the open questions in high energy physics, and yet it opened new ones. So for example, now we can wonder if, or we can ask ourselves if there is a coupling of the Higgs with dark matter. The mass has been measured, that now we can ask if this is a fine-tuned parameter in the theory, while we see this hierarchy of particle masses, or if there is any role of the Higgs in the neutrino sector, and for instance, what causes the origin of the Higgs potential. So today, I think there is a strong motivation to explore beyond standard models, especially in all directions of the phase space. So following on these, the RAN2 legacy data also puts very strong constraints on beyond standard model particles. And this is especially true for searches that assume that beyond standard model particles promptly decay, or that have the final state objects experimentally invisible. So this would be Mysinity. And just to give an example to illustrate this is the overview of SUSY results, constraints on stops, bottoms in various final states as a function of the mass. And you can see that all the constraints all the way to the TeV scale. Now, I should also say that this assumption is often driven by convenience rather than by physics consideration. And just to give an example is that long-lived particles also exist in the standard model. Now, recently, the searches are putting more emphasis in experimentally challenging signatures. And one of the examples would be long-lived particles. And this is the topic of this talk. So long-lived particles, or in brevity LLPs, are predicted in common beyond standard model scenarios like SUSY, additional neutrinos, dark sectors in various regions of the model phase space. For example, they're manifested when there are decays that they are mediated by heavy virtual mediators, or when you have a BSM spectrum with nearly mass degenerate states, or when the model features small couplings to the standard model. As a consequence, in order to cover the whole phase space, all the searches need to be performed considering an extra parameter that is the lifetime. Now, for us as experimentalists, we treat the lifetime as a free parameter. And this is because we don't want to make assumptions on the parameters of the BSM. And this choice can lead to very interesting features. And this is because the exponential decay follows an exponential distribution, so you can have decays of long-lived particles in various subdetectors. And as a consequence, you can have a given LLP signal leading to detectable signals in very unconventional ways. And as a result, you can have a plethora of long-lived particle experimental signatures. So in principle, the signature strongly depends on what kind of LLP you might have. In particular, what is important is the lifetime or the charge of the long-lived particle, as well as the decay products. And each of these combinations would define a potential experimental signature. Usually they are illustrated in this kind of diagrams. This is a summary of various LLP signatures. And most of them, in order to be explored, they need a dedicated search. So CMS have searches for all these kind of signatures. Because of time, I cannot cover all of them. And in this talk today, I'm going to pick a few examples. So first, I'm going to focus on searches into displaced leptons. And for this, I discussed 3 searches: covering cases where the dileptons come from a common vertex or not. And then in the second part, I'm going to discuss LLP decays into hadronic final states. So this will be displaced dijets and displaced vertices. Now, all long-lived particle searches have something in common, and is that they cover unique and often orthogonal BSM phase space. But at the same time, they are very challenging experimentally. In particular, they often use dedicated level 1 HLT or reconstruction algorithms. And the reason for this is that standard algorithms usually assume standard model objects. And for example, is that one assumes that decay products are produced within the beam spot. In other cases, the searches use custom data sets. So for instance, you might need to access to raw data to get information from detector level variables, like you want to retrieve information of the heat positions. Or you might want to use data reconstructed at HLT, and this I'll discuss in a minute in the context of the scouting search. Most of them deal with non-collision backgrounds, and this I want to highlight with these two examples. In the first one, this is a nuclear interaction veto map. And what this search is doing is to remove displaced vertices that are located in dense areas of the detector. And these are not coming from the signal. This is just interactions with detector material. And this is a dangerous background. The second example shows here in yellow a cosmic ray muon traveling through CMS, and this can lead to a displaced vertex several meters away from the interaction point. So this is another powerful, dangerous source of background in long-lived particle searches. Finally, these searches also deal with unconventional signal simulations. And one of the challenging things is to validate the signal efficiencies with real data, as there are no real sources of displaced objects in the standard model. In addition, because the signal efficiencies might have various dependencies on many variables, it is usually not so easy as in prompt searches to do reinterpretations. So the typical approach in terms of signals for long-lived particle searches is to use benchmark models. These are simple models that try to capture the main features of the signal in the detector. And I'm going to try to discuss briefly the main ones that we use in CMS. In the first block, I'll discuss the ones that are inspired by dark sector models. Typically, they consider long-lived neutral mediators that have macroscopic lifetimes due to the small couplings with the standard model. And one example of this would be a dark photon that mixes with the standard model. Now, the typical production mechanism that is considered in this benchmark model is the pair production in standard model Higgs decays. So this is the diagram that you see in the top right. And for this production mechanism, one important parameter is the branching ratio of the Higgs to pair of long-lived particles, because this controls the signal rate. And then the branching ratio of the Higgs to the final state, the lifetime, and the mass define the experimental signature. And we have searches in various final states. Now, usually searches consider the X, the long-lived particle, to be spin 0, and then it's usually denoted as S, or spin 1, and it's denoted as dark photon C dark. Now, other class of searches probe low mass dark mediators phi in hadron decay. So this would be lower masses, and this is a typical B to phi X signal. In the context of SUSY, typically the searches assume a charged supersymmetric partner, and these are inspired by R parity violating or gauge mediated DMSB SUSY benchmark models. And a typical scenario is the pair production of leptons that they lead to displaced leptons and a gravitino that it's in form of missing ET in the detector. So the first search that I want to discuss is the dimeons with scouting. And the key feature of this search is the data set, that is a custom data set, because it uses data collected by height rate triggers. And what we do in these events is we only save limited information that is reconstructed at the HLT. So this to reduce the event size. Now, the events that make up in this data set pass the level 1 double muon triggers, and they have at least 2 muons with PT larger than 3 GeV. The signature will be at least one displaced dimuon pair. And this is done by requiring that the dxy significance to be larger than 2, and the dxy significance divided by this term here, that this is the reconstructed proper time, to be larger than 0.1. In addition, the dimuon momentum and the transverse decay are required to be in the same direction. And in addition to the reduced backgrounds, there is what I discussed, this veto of the detector material. Now, the idea is to search for a narrow resonance in the dimuon invariant mass distribution, and this is done in beams of the transverse decay length, the dimuon PT, and the muon isolation. So here the plot shows the dimuon invariant mass distribution in various LXY beams. So in orange, we have prompt-like events, and as we go further down, we go to up to 10 centimeter in displacement. And the idea is to look for a peak in these distributions. Now, in order to evaluate the background, what is used is the same data in a sideband window around the probed signal hypothesis. So this is done in all these signal region beams, and there is no signs of any peak in the invariant mass distribution, and the results are interpreted in Higgs to C dark here on the left, and B to phi X signal models. Now you can see as a function of the mass in both cases that there are some gray bands, and these are regions that are not probed by the search, and this is because they overlap with known standard model resonances. Now, for the first model, Higgs to C dark, the most sensitive signal regions include events where the dimuon momentum has a PT larger than 25 GeV, so this is a quite high PT signal, while for the case from B hadrons, they have a lower momentum. In addition, for the C dark model, you can have a second long-lived particle leading to a second displaced dimuon, so there is a separate signal region where there are no events that have been observed. So now, if you look carefully, you would see that the vertical axis in the results is different for the two models. So in one case, you place limits in the branching ratio of Higgs to C dark, and then C dark to mu, while in the other case, then you put constraints on the branching ratio of B to phi X, and then phi to a dimuon. And just these are two limits for a 10 millimeter lifetime, so this is quite short-lived. But this is very interesting because this is actually the first search for long-lived particles that uses a scouting data set in CMS. Now, I'm going to change to a more inclusive search, also with displaced leptons, and this one is very interesting because it's inclusive in a sense that it doesn't have any requirement. It has minimal assumptions, so there are no requirements on number of jets, missing ET, lepton charges, or the presence of a common vertex. And at the moment, this is the only search for displaced electrons of 13 TeV from CMS. Now here, the signature involves at least 2 isolated displaced leptons. And you can see here that now the PT requirements are higher depending on the year and the lepton from 35 to 70. And these are driven by the trigger requirements. Now the displacement is ensured by requiring that the dxy is to be within 100 micrometer and 10 centimeter. Then in this search, this plot shows the signal regions. You see that they are divided by the leptons in the final state. And then they are further subdivided in categories that correspond to high or low lepton PT, and then going from 1 to 4, increasing the dxy of the leptons. And then once you go to the end, you see that the background reduces. This is where you have the most sensitive beams. Now in this search, the background, it's coming from displaced leptons coming from tau decays and heavy flavor decays. And these backgrounds here in blue are evaluated using the same data, but in a region where you invert this requirement for one of the leptons. And then this background is validated using the simulation. So now this search is interpreted in various BSM scenarios. Starting on the left, this is for the dark mediator, similar to the scouting data, but in this case, we have results for the electrons, and this is what they said that these are the first ones that we have at 13 TeV. Then at the same time, you can use the same search to scan of long-lived stops as a function of the lifetime. So you can see that at 1 centimeter, you can probe up to 1.5 TeV. And this is about a 700 GeV improvement with respect to the previous result. And then finally, this is on the right, these are constraints on leptons. And you can see for different colors, staus, selectrons, and muons. And this is the first search that we have for long-lived leptons using displays leptons. So you can see that these are three different models, but they are all probed with the same search. And this is what I mean at the beginning, that this was a very inclusive and is very powerful. And I'm very curious to see what other reinterpretations can be done with this search. So now I'm going to switch gears and put the leptons aside and go and talk about hadronic showers. And here, this is a smart idea, where the idea is to use the muon detectors to tag a hadronic shower. And this search is using the end cap. So now we're going to go several meters away. Before we were really close to the interaction point. So between 7 meters and 11 meters. And then in R, in the radius between 3 and 7 meters. So the idea in this box is to look for a cluster of heats with large multiplicity. And this is a cluster of heats because this is a hadronic shower in a muon detector. So this cluster has some requirements on the quality on the identification. And in addition, it's required that the time of the cluster is within one bunch crossing with timing requirements. Then this cluster is vetoed if it is matched to a jet or muon shower to reduce backgrounds. And this search is using events triggered by the Meissonier-T trigger. And what is required is that the Meissonier-T is aligned with the cluster. And this is to ensure that the Meissonier-T is coming from the cluster. And this is what you expect from a signal. Now, this is the most discriminant variable, that is the number of hits of the cluster. And you can see that the signal clusters at very large number of hits. And then the background here in blue clusters at small values. And in this search, the background is coming from long-lived standard model hadrons producing pile-up interactions. This background is evaluated inverting the requirements on the number of hits on the delta phi, and it's validated using out-of-time pile-up or events failing the cluster ID. So the results in this search are interpreted in various final states. So you have quarks, so DD or BB bar, they're pretty similar, or into hadronic taus. And you can see, so each of the curves corresponds to a different mass from 7 GeV to 55 GeV. And you can see is that pretty much the sensitivity does not depend on the mass, and even whether you have quarks or hadronic taus, which makes the search very powerful to different final states. In fact, the sensitivity is dominated by the geometrical acceptance and the trigger efficiency. And now, just to highlight where this is powerful is especially once you go to 7, 15, and 40 GeV. These are the first three curves. These are the most stringent limits at high lifetimes that are coming from this search. So this is a really powerful approach. So trying to wrap up, let's try to put the three searches that I described in the same plot. So we have here in purple the dimuon scouting. So this puts the stringent constraint for the dimuons. You can see that there is still some room for improvement at the higher lifetime. So this is probably where we will see more improvements in the future. For the electrons here in yellow, you have lower constraints, especially at the high lifetime. And then for the hadronic showers, this is the blue curve here. You see that it probes much higher lifetimes, and it's not as competitive as leptonic final states. For hadronic final state, the region that is harder to explore is the short lifetime. So there's all the searches I haven't discussed yet, but this is the area where hadronic searches are trying to improve now. So Now I'm going to change to a different production mechanism. And this is when you have the long-lived particles produced in association with standard model prompt objects, for example, prompt leptons. And this is very interesting because there are BSM theories that are very well motivated that predict this signature. And one of them are the heavy neutral leptons. So this would be the case where you can have a W boson decay into a lepton and a neutrino that mixes with the mixing parameter. Here is the V, depending on the neutrino species, into the HNL that is long-lived and leads to a displaced vertex. Now, the lifetime of the HNL depends on its mass or in the mixing parameter with this proportionality. But the most interesting regime is the low mass and low coupling regime, where you can have macroscopic lifetimes. It is also possible to have not only one, but two prompt leptons. So this would be the case where you have, for instance, the Higgs boson produced in association with the C boson. And this is interesting because you can use the leptons from the C boson to tag the event and then search for low mass long-lived particles. So what you would see now in these two searches is that where they shine is when you look at the low masses, and this is thanks to the presence of the prompt leptons. So for the first case, for the heavy neutral leptons, the final state involves 3 leptons, and one of them has to be prompt. And this is the one with the hardest PT requirements because this is the one that triggers the event. And this lepton is going to be recoiling against a displaced dilepton pair with much reduced PT requirements, and then with the DXY requirement inverted with respect to the prompt lepton. Now, these 2 leptons are fit together to a common secondary vertex, and all 3 leptons are isolated. In addition, the event is required to not have beta jets, and then the 3 lepton invariant mass has to be compatible with the W, because in the model everything was coming from the W. Now the signal regions are split into lepton flavor and charges. Then they are further subdivided into the dilepton invariant mass and categorized in the transverse displacement for the different leptonic combinations. So the most sensitive beams are the ones at the highest displacement. You see them at the end of each of these block of beams. Now the background in green here is coming from non-prompt backgrounds originating in the same hydro decay. And these are evaluated using, like in the other searches, background enriched data, and they are validated using events failing the event caps. Now, as I mentioned, the search regions were split by lepton types and charges. And one of the reasons to do this is to maximize the sensitivity to various HNL scenarios. So for example, if the HNL is of Dirac type, then the lepton number is conserved, and then the prompt lepton with the second lepton are going to be always opposite sign. While if the HNL is Majorana, then the lepton number can be violated, and then you can have lepton 1 and lepton 2 to be opposite sign or same sign. So depending on the model, various signal regions will be populated differently. In addition, the prompt lepton can be the electron or a muon. And this is very important because when the lepton is the electron, then you would be putting constraints into the mixing with the electron neutrino, while if it's for the muon, this would be the muon neutrino. Now, the constraints are placed as a function of the mass, and you can see that they have a similar shape, and in this shape where you have high sensitivity at large masses and then it decreases is coming from the relation that I discussed here of the lifetime with the coupling. So once you go to the bottom left corner here, essentially the HNL is too long-lived and then it escapes the tracker detector. So this brings me to the last search I'm going to discuss, and this is similar to the previous one experimentally, but with the difference that now you can have 2 isolated prompt leptons. And in this case, they're going to be compatible with the C boson. In addition, the dilepton momentum is going to be larger than 100 GeV, and the idea is to look for a displaced jet within the tracker volume. And the jet is going to be tagged using track level variables like the primary vertex compatibility, the DXY significance, or the missing angle. So here, this plot, what it shows distributions for various validation regions and the signal region at the end. And you can see that the main backgrounds are C+ jets in brown and TD bar in orange. And these backgrounds are evaluated in events that fail the dilepton PT requirement or using E-mu events instead of EE or mu. And they're done together with transfer factors measured in Monte Carlo. Now the validation, and these are the validations from 1 to 7, are done inverting the cuts entering into the tagging of the jets, these variables here. And these are all background enriched, so you can see that there is a good agreement. While once you go to the last bin, you have the lowest background, you have the largest signal, and this is the most sensitive bin. You see that there is a good agreement with the prediction. So in this search, the results are interpreted in the context of the production of the Higgs, and then the long-lived particle decays to hadrons. And here I want to stress, so these are the results for the search, but I want to really focus on the low mass, because at low mass, for the lifetime that is proved here, so this is a few millimeter displacement, one can compare it to the search that I discussed of the hadronic showers. This is meter displacement. So you can see that it complements that search in the low lifetime regime. And this is where the power of the prompt leptons, that you can use it to explore the low mass, low lifetime regime, where I said that the constraints were reduced. Now, the problem of this approach is that the sensitivity is limited by the signal rate, because you need the C boson, the C boson. So the gluon-gluon fusion is 75 larger than the CH. And then in addition, you have a further suppression from the branching ratio to the leptons. So this brings me to the summary and the outlook. And just want to stress one more time that long-lived particles appear in traditional BSM scenarios in different regions of the model phase space, and this has to be explored experimentally. Now, CMS has an extensive program for long-lived particles targeting a wide range of lifetime masses, charges, and final states. And today I picked a few examples. Now you can click in the link, go to the CMS website, you would find all these searches, and I picked a summary plot that includes many more searches that I discussed. And what I want to stress, and this is as a function of the lifetime, is that you see that there are wide spaces. And this is because some areas are experimentally very challenging. So this is a field of long-lived particle searches that is in continuous R&D. And this is because there is plenty of room for new exploration for round 3 and High Luminosity LHC. So one should expect novel ideas and, for example, dedicated triggers or new searches targeting uncharted BSM phase space. So at least I think, in my opinion, there will be exciting times ahead for long-lived particle searches. So,
Thank you, Alberto, for this wonderful and insightful talk. So now the floor is open for questions. Yes, Prabhat, can you please unmute yourself and ask the question?
Can you hear me?
Yes, we can hear you.
Could you please go on slide 14? So here, why are the limits less restrictive for very small C tau? So I can understand for larger C tau it will be much less restrictive, but why for small C tau it's less restrictive?
So one has to first compare compare different final states. So usually when you have leptonic final states as more C tau, like here you have very strong constraints, while you go to hadronic final states, you have very low sensitivity. And the reason for this is that triggering on low lifetime hadronic final states is very challenging. So this limit here corresponds to the production of a C boson and displaced jet. So this is the last search. So effectively, you have to wait until you produce the LLP with prompt leptons from a C to record event. So you lose a lot of signal efficiency this way. Now for this search, this covers hadronic decays in the muon detector. So you can explore high lifetimes because they have to make it to the muon detectors, but to do it in the tracker, then the background from QCD is too large, and then it becomes very hard to explore. It's one of the hardest regions to explore in hadronic final states, because you can see in leptonics this is not a problem.
Okay, so so suppose you take one scenario, say diamond scouting. So there is a dip. So the limits are less restrictive at like very low, say 0.1 mm. So why is that? I was just wondering.
You mean this part here, no?
Yeah.
Yes. So effectively, the search is bound two ways. So let me just go to this slide. Yes. So this is the spectrum split in displacement in LXY. So you can see that the backgrounds are much larger at small displacement. So, and in addition, you have requirements on DXY. So effectively, in the short lifetime regime, you have more background that you have to suppress with displacement caps. So you start to lose sensitivity rapidly. And then as you move further out, so this would explain this end. And then as you move further out, what happened is that the decays happen beyond the pixel detector. So you don't reconstruct the tracks anymore.
Okay, I got it. Thank you.
It's pretty much the same for all curves. You see that your lifetime is usually coming from the displacement regime, with the exception of this one.
Okay, great. Thank you.
Well, I can see another question from Ritesh. So can you please unmute yourself and ask the question?
Yeah. Can you hear me?
Yes, we can hear you.
Yeah. So for the decay in the muon spectrometer search, why do you use only the end cap part of the detector?
This is a very good question. Let me just go to the slide. Right. So this clustering the hits, it's a non-standard thing. So this is one of the analyses that it uses what I said in the challenges, raw data sets, because you have to access the hit information. So developing the counting of the hits, it was really a novel idea, and it was developed first in the end caps. There is work coming into the barrel. This is in the making, but it will come in the future. So in principle, this is one of the areas to improve, to extend this kind of ideas beyond the end cap. But yeah.
Okay, so it can be done, right? I mean, in the barrel,
it can be done. I don't want to enter into technical details why it was easier to start this clustering. But the long story short is that it can be done. It needs more exploration, and because these things, this is the first time that this is done in CMS, but it will be done in the future, certainly.
Okay. Thank you.
Well, it seems there is no further question. So let's thank Alberto for this wonderful talk again. Thank you, Alberto.
Thanks.
Seconds.
Thank you, Alberto.